Hello dear students, welcome back. As you know, in a previous lesson, we stopped here in question 36 in chapter review. So the question says, a 0.1 kilogram meter stick at it is 40 centimeter marked by a string attached to the ceiling. A 0.7 kilogram mass is hangs vertically from the 5 centimeter mark. Okay, so a mass is attached somewhere on the meter stick to keep it horizontal at both rotational and translational equilibrium. The second mass is unknown. If the force applied by the string attaching to the meter stick to the ceiling is 19.6 Newton, determine the following. A, the value of unknown mass, the second mass. B, the point where the mass attached to the stick. It is at the distance of the second mass that attached to the stick. Okay, let's open a new slide, and now I'm going to solve this question. Okay, what we have? We have a meter stick. Okay, its length is 1 meter. It means that 100 centimeter. Okay, assume that this is 0 and here is 100 centimeter. Okay, so the mass of the meter stick is located, because the meter stick is uniform, its center of mass is located at the middle. Where is the center of mass of uniform object? The center of mass and center of gravity for the uniform object is located exactly at the middle. Okay, so the mass of meter stick is 0.1 kilogram. Okay, I mark it at 50 centimeter. Okay, so the question says, when the beam is attached by the string and mark it at 40 centimeter. Okay, so this meter stick is suspended by this tension force, okay, at 40 centimeter. Okay, the tension force that attaches to the ceiling, okay, located at 40 centimeter. Okay, so if the mass is suspended at 5 centimeter, okay, at 5 centimeter, this is M1 is equal to 0.7 kilogram, okay, attached to the meter stick at 5 centimeter. At where? At 5 centimeter. Okay, so where should be the second mass suspended to the meter stick to keep the balance of the meter stick? Absolutely, the second mass is located into this other side, this side. Okay, why? To make the balancing. Okay, because if we suspend the mass in this side, okay, the meter stick try to rotate. Okay, it doesn't be a translational equilibrium. So that is why we have to suspend the second mass here, but the second mass is unknown. I don't know what is the value of this mass. Okay, we have to find it. We have to find the mass when suspected to the meter stick to make a balance. Okay, translational equilibrium and rotational equilibrium. To find mass, always you have to use or apply translational equilibrium. Net force is equal to 0. Okay, so it means that you have to select the axis of rotation. Assume that this is axis of rotation. Okay, assume that what is this? This is axis of rotation. In that case, because the axis of rotation is located at the end, so we have to equalize all upward forces to all downward forces. How many upward forces do we have? Only one force. Ft, 19.6 Newton. Okay, 19.6 Newton is equal to how many forces? Downward forces do we have? We have 3 gravitational force, because mass, gravitational force is equal to what? Is equal to m1g. The gravitational force for the meter stick is equal to mass times gravity. So the gravitational force for the second mass is equal to m2 times gravity. When mass is given, you can convert to the gravitational force multiplied by the free fall acceleration. Okay, so that is why we have to write down fg1 plus fg2 plus fg of meters t. Okay, bring down this 19.6. fg1 is equal to what? Is equal to m1g m2g, the mass of the meter stick times the gravity. Okay, so we can take a common factor for g because g is the same. Okay, sorry, g because it's the same, we have to take this gravity as a common factor. What does remain here? m1 plus m2 m1 plus m2 plus the mass of the meter stick. Okay, so 19.6 is divided by 9.81, so it goes to the other side. Okay, this gravity, which is equal to 9.81. What does remain? m1 was given 0.7, m2 unknown. Okay, m2 unknown plus the mass of meter stick 0.1. 19.6 over 9.81 is equal to 0.8 plus m2. You can rearrange the equation. m2 is equal to 1.2 kilograms. So the mass that's suspended by the meter stick is equal to what? 1.2 kilogram. This is the mass of the object that's suspended by the meter stick. Okay, but in this question we don't know at which position exactly the second mass suspended by the meter stick. Okay, so we have to find this distance. Okay, we don't know at which mark the second mass is suspended to the meter stick. Now I'm trying to find the distance of the second mass when attached by the meter stick. Okay, the second unknown of the question the point where the mass attaches to the stick. Okay, the point of the second mass when attaches to the stick. Okay, so it means that this distance, okay, d2. Okay, what is the value of d1? d1 is 5 centimeters from the axis of rotation, which is equal to 0.05 meter. What about the distance of the meter stick, the center of mass of the meter stick? Because the meter stick is 1 meter, it is center of mass located at the middle, so the distance of the meter stick is equal to 0.5 meter. What about the distance of the tension force marked at 40 centimeter, which is equal to 0.4 meter from the axis of rotation? What about d2? d2 is unknown. Every time to find the distance, you have to use the rotational equilibrium. Okay, in the rotational equilibrium, net torque is equal to what? Is equal to 0. Because the axis of rotation is located at the end, you have to equalize all upward torque to all downward torque. Okay, how many upward torque do we have? Only the torque of the tension force. How many downward torques do we have? 3. Torque number 1 of the first mass, torque for the second mass, and torque for the meter stick. Okay, now the equation of the torque is equal to what? Ft times distance for the first one, Fg1 times d1, for the second one, Fg2 times d2, Fg of the meter stick times the distance of the meter stick. Okay, bring down this Ft times d. Fg is equal to what? Is equal to m1g d1 plus Fg2 is equal to what? m2g d2 plus fg of the meter stick is equal to the mass of the meter stick times gravity times the distance of the meter stick. Okay, now replace the number. Ft was given 19.6 times distance of the Ft is equal to 0.4 from this end. So G is the same. We can take a common factor, which is equal to 9.81. Okay. Common factor, because it's the same, you can take it out. So what does remain? M1. M1, 0.7 times D1, 5 centimeter, which is equal to 0.05. Okay. Plus M2. We didn't have M2 at first, but we found it. 1.2. Okay. Times D2, unknown. Okay, plus M, the mass of the meter stick, 0.1 times distance of the meter stick is located at the middle, so that is equal to 0.1 times 0.5. So you can rearrange this equation. It becomes like that. 0.6 times 0.4, 7.84. So 4.7 okay, 9.81. This is becomes 0.035 plus, okay, 1.2 times D2 plus 0.1 times 0.5, which is equal to 0.0. D2 is equal to 0.596 meter. So it means that the second mass is located at where? At 0.596. It means that 59.6 centimeter. The second mass is suspended at this point. 59.6 centimeter. Okay. This is question, I think it was question 36 is in chapter review. We finished it and we solved all the questions that related with the translation and rotational equilibrium, okay? Now we are going to solve the questions of the section review of section 2 in chapter 2. Question 1, it's a very good question. It has been brought in the Wizaria exam many times. Listen carefully, please, okay? At which of the 7 positions indicated in this figure should the supporting pivot be located to produce the following? A net positive torque. Net torque is positive. B, net torque negative. C, no rotation. What do you mean by no rotation? It means that net torque is equal to 0. In which pivot the net torque becomes positive? How many pivots do we have? We have 7 pivots, okay? And we have 2 mass that attached by this beam, okay? The first mass, it is a force is 150 Newton. This is Fg1. Assume that this is Fg1 and this is Fg2, okay? Fg1, it is direction is clockwise, so that is why torque number 1 becomes negative. And Fg2, it is direction is counterclockwise, torque number 2 becomes positive, okay? So it means that we have 2 torques in opposite directions. So to find the net torque between these 2 gravitational forces, we have to subtract each torque, okay? Now, how can you solve this question? Listen carefully, please. It is a very good question, easy question, okay? So to find a net positive torque, assume that this point G, okay, is the balancing point, okay? Or so we assume that at G net torque is positive, but we have to you have to show your work that Y at G net torque is positive, okay? Let's get started to solve this question. Net torque is equal to what? Net torque is equal to torque number 1 plus torque number 2. Okay? To find torque number 1, the torque of the first object, Fg1, is equal to F1 because it is clockwise direction, so that is why it is negative F1 D1. Okay? At which point? At G. At point G. Okay? So you have to test all points to make sure which point has net positive torque and which point has no rotation, at which point or which later has no negative torque, net negative torque. At point G, okay? Torque number 1 is equal to negative F1 150 times. At point G, assume that the distance between these two pivots is 1 meter. So what is the distance from point G to the first gravitational force? Is 1 meter. What about for the second force? The distance of the second force from G is equal to how many meters? 1, 2, 3, 4, 5, 6, 7. F2 is 7 meters away from point G, but F1 is 1 meter from point G. 150 times 1 is equal to negative 150 Newton meter. This is torque number 1. Torque number 2 for the second mass, second gravitational force, is equal to positive F2 D2. Why this is positive? Because it is rotate counterclockwise direction. So that is why it's considered to be a positive. Okay. F2 was given 50 times D2, as I told you. D2 is equal to what at point G? Is equal to 7 meter. Okay. Is equal to 350 Newton meter. Okay. How many torques do we have? 2. How can you find the net torque? Torque number 1 plus torque number 2. Net torque, torque number 1, negative 150 plus 350 is equal to positive 200 Newton meter. So it means that at point G, net torque is positive? Yes, of course. So at point G, the net torque is positive. Okay, let's check the point F. What about point F? Maybe point F also has net positive torque. Okay, so that is why we have to find the net torque at point F. At which point? Point F. At point F, the distance of the FG1 to the F is equal to how many meters? 2 meters. This is D1 at point F. But for the FG2, the distance from F to the FG2 is equal to how many meters? 1, 2, 3, 4, 5, 6. So D2 is 6 meters. D1, 2 meters. Okay? Let's write the equation. Net torque is equal to torque number 1, torque number 2. Torque for the first gravitational force, because it is clockwise direction, it's always negative. Fg1 times D1, okay, which is equal to what? Fg1 150, negative 150 times 2 is equal to what? Negative 300 Newton meter. What is this? This is the torque of 150 Newton when the pivot is located at F. When the balancing or the pivot or the axis of rotation is located at which point? At F. Okay. So what about the second torque? The torque of 15 newtons is equal to positive. Why positive? Because it is counterclockwise. F2 times D2. Torque number 2 is equal to F2 50 times d2, 6 meter, as I mentioned before, is equal to positive 300 Newton meter. Now, net torque is equal to what? Net torque is equal to negative 300 plus 300 cancelled is equal to 0 Newton meter. So at which point there is no rotation? At point F. Why? Because at point F, net torque is not positive and is not negative. It means that the point F has no rotation. The balancing point between these two different mass is located near the heavier side or lighter side. The balancing point for non-uniform object is always located near the heavier side. This is heavier side, this is lighter side. So the balancing point is located near the heavier side. Which point is the balancing point? It means that there is no rotation at point F. Which point has positive net torque? Point G. Point G. Which point has no rotation? Point F. So what about the net negative torque? If F is 0, G is positive, the other points, all of them becomes negative. So A, B, C, D, and E has net negative torque. Okay? For example, at point E, okay, I solved with all of them. At point E, torque is equal to 150 times 3 is equal to, look, for point E, how many meters away from the 150? 3 meters. How many meters from 50? 1, 2, 3, 4, 5 meters. 3 times 150 is equal to negative 450 Newton meter. For the second force, which is equal to 50, 50 times 5 meters is equal to 250. Negative 450 plus 250 is equal to negative 200 Newton meter. The other points, all of them becomes negative. Okay? Question 2, describe approximate location of the center of mass for the following objects. A meter stick, its center of mass is located exactly at the middle. A bowling ball near the center of the ball, away from the finger's hole, because the finger's hole is empty mass, so it is lighter, so that is why it is away from the finger holes. An ice cube, the center of mass of ice cube is located at the center of the cube. A donut, the donut, its center of mass is located at the center of the donut. A banana, look at, this is banana, okay? The center of mass of banana is located also at the middle. For example, this is banana, A, B, C, D. Which point is the center of mass of the banana? B or D? Both of them center, but B is correct. Why? Because the center of mass of the banana is located at the middle along the inside curve, not outside curve, be careful. Okay, along what? Along the inside curve. So a student say the moment of inertia and mass are the same quantity. Explain what is wrong with this reasoning. So this is completely wrong, because the mass and the moment of inertia is not equal. They are completely different to each other. Mass is the property if the body that resists the change in translation is the property of the body that resists what? Change in translational motion. But measured in kilogram. But moment of inertia is the property of the body that resists change in rotational motion, measured in what? Kilogram meter square. Mass resists the change in translational motion, but moment of inertia resists the change in rotational motion. Okay? Question 3, identify which, if any, conditions of equilibrium holds for the following situation. A bicycle will rolling along level highway at constant speed. Because the bicycle is moving with constant speed, V initial equal to V final. And also omega initial is equal to omega final. Net force 0, net torque also 0. So it has both conditions, rotational and translational. Why? Because the bicycle is rolling with a constant speed. When velocity is constant, angular speed also constant. A bicycle parked against a curb. When the question said a bicycle parked against a curb, in that case, there is no speed, there is no angular speed. there is no velocity, it means that the bicycle also has both translational and rotational equilibrium. A tire on a braking automobile that is still moving. When the tire is still moving, but by using a braking, okay, the brake, it goes to slowing down the car, so that is why the velocity decreases. When velocity decreases, acceleration is not equal to 0. Net force also not equal to 0. So we cannot say this object has translational equilibrium. The object has no translational equilibrium. When this velocity decreases, what happened to the angular speed of the tire of the automobile, of the car? The tire also, angular speed of the tire also decreases. Angular acceleration can never be 0 in the case of decrease or increase. So in that case, we cannot say also the object has rotational equilibrium. So finally, it's neither translational or rotational equilibrium. A ball traveling through the air. Traveling ball, the question doesn't say rotating. When the question says traveling, it is not without rotating. Because the ball has no rotation, net torque is 0. Okay? Net torque is what? Net torque is 0. Because the ball doesn't rotate. It has rotational equilibrium. In the air, because the air resistance affected on the ball and the gravity affected on this ball, we cannot say net force 0. Net force is not equal to 0. Why? Because the ball traveling in the air. The air resistance affected on the ball. But because the ball doesn't rotate, so that is why it has only rotational equilibrium. Okay? So this is question 4. It's easy question. We have two force in these two sides. What is unknown? The normal force of the pivot that acting upward is unknown because the axis of rotation is located at the middle. You have to equalize all the right torque to the all left torques. Okay, you can rearrange the equation and you can find the normal force of the pillar that exerts on the seesaw. Okay. Why would it be beneficial for the bicycle to have a low center of mass when the ride around isn't there? To reduce the distance. Why? Because torque is equal to what? Fd. When the distance from the axis of rotation is decreases at constant force, what happened to the torque? The torque also decreases. So when the torque decreases, it keeps the rider to avoid bike tip it over. Okay? Because the rotational arm distance from axis of rotation decreases when the center of mass be at a low point, which decreases the bicycle's inertia. So the torque on the bike is less to tip it over. Okay? A bicycle designer recently modified a bicycle by adding cylindrical weights to the spokes of the wheels. He reasoned that this would make the mass of the wheel on average closer to the axle or the axis of rotation, in turn making the moment of inertia smaller and wheel easier to rotate. Where did he go wrong? The wrong is here in this question. The designer, okay, he added many cylindrical weights, okay, because I is equal to what? Is equal to mr squared for the ring. When mass increases more and more, what happened to the moment of inertia? Also increases. Even if the radius is decreases, because the designer, they brought some external mass, not the mass of the wheel. Okay, but if the designer is trying to closing the mass of the wheel itself close to the axis of rotation, in that case the moment of inertia decreases and it goes to rotate easily. But extra mass, it goes to increasing the moment of inertia. The mass increases a lot of, so that is why the moment of inertia also increases, and it doesn't goes to decrease the moment of inertia, so it is difficult to rotate the object. Okay, so this is the section 2 in chapter 2. We finish the section 2. Inshallah, in the next lesson we will start explaining and finishing the section 3 in chapter 2. Hope you get benefited, and thank you for listening.